suppose else you have like a new strategy as a member of the organizing committee of the seminar, and call the meeting to order, and introduce the speaker, James Freitag, who is going to talk about differential algebra. I've known this man for a while. I claim responsibility for his interest in mathematical logic.
It's true.
Oh.
Okay. All right. Okay, thank you. Okay, so, all right, so yeah, the problem I'm going to talk about, I guess, is in differential algebra generally, or, but you'll see what it has to do with model theory, of course. Okay, but the basic problem is this. Okay, so let me just talk a little informally at the beginning. Suppose you're given a system of differential equations in some number of differential polynomials over some differential field. It doesn't really matter. And maybe some inequalities as well. Okay, and the question, or one question, is, so these are differential polynomials. Okay, so formally speaking, they're polynomials in the variables and their derivatives, and okay, we'll get to more of this. But the question is, and so what they cut out is of course a definable set or a constructible set in this case in the Colchin, what's called the Colchin topology, where you take the closed sets to be zero sets of polynomial differential equations. And so the question is, maybe a bound, or what is the degree of the Zariski closure. Of the definable set, I mean the one determined here, okay? And
can you be specific? What does degree mean exactly?
Well, okay, so in this talk, the degree of okay, so everything is going to be affine first. Everything will be over a field. In my talk, it's not necessary, but I think it's better for simplicity in this audience. And the degree of an irreducible variety will just be the number of points in the intersection with codimension many generic hyperplanes.
Rewrite
so
that.
It's
okay, or the leading coefficient of the Hilbert polynomial.
well, that's only the same with the Cohen-Macaulay.
Oh, the leading coefficient.
Yeah. Okay.
All right, that's easier.
Okay.
Yeah. And if it's not Cohen-Macaulay, that degree, the first degree would be bigger.
Okay.
Which one?
The first one would be bigger.
The geometric one.
Yeah. Yeah, that's the that's bigger. That's actually an equivalent condition with Cohen-Macaulay. Yeah. We have to be careful with that.
Okay. All right. I'll take that as my definition. And which one? The geometric.
The geometric one.
I'll take the geometric one.
Okay. Mm-hmm.
And when the set is not irreducible, then I'll take it to be the sum of the degrees of the components.
Yeah. Okay.
So I want to count lower dimensional components.
Oh, so
I want to count those degrees.
Okay.
So I want to be clear about that. That's important.
All right.
Okay.
So you're putting the lower component count the same as the same weight with the other.
Yes.
Okay.
Yes. So I calculate the degree to be the sum of the degrees of the irreducible components. That's my definition for this talk. Okay. It's just a definition. I'm not making claims that that's like the best thing to consider, but for the purposes of this talk, that's what you want to consider. Okay. So So a special case, which is already where almost all of where all of my interest in this problem came from, is in the case that this is a finite set, that this definable set here is actually finite. Okay, and so okay, you may say something in a minute, but just wait. Okay. So this is a special case, and you may say, well, okay, of course you can do this, right? Because because this is a first order property, and you can say some things like that. But what I want is a bound for the number of points, which is the degree, the number of points in that finite set, based only on basically what I would call the shape of these equations. So basic invariance of these equations, like the order and the degree of the equations. Okay, so I would like, okay, I mean, I'm being a little loose here, but I'll give specific bounds later. I would like to get bounds on the size of this finite set based on the order of the differential equations which appear here, the number of variables which appear here, and the degree of the equations which appear here. Okay? All right. So, and it's not, I mean, it seems to me non-trivial to determine when you're even in this special case. I mean, that's non-trivial. So, I mean, here's an example, which you might not expect. So, I'll explain some of the notation. I calculated this example on the plane here. I'm pretty certain that it's correct. Okay. So
where were you coming from? So how good the
I was coming from Berkeley.
Okay, so it's good for you. Yeah, that
Was it a red eye flight?
It was a red eye, though.
That's very suspicious.
It's a red eye. So here's something that fits. I mean, this is an extremely simple case of what happened here. Okay, and the question is, I mean, it doesn't look like to start that there's any reason to believe that there would just be finitely many solutions to this equation. In fact, I claim there are. Okay, so let's see how to do that. So what I would say one should do is the same thing that you should always do if you're trying to do something like this and you just have one equation. You should differentiate it. There's not much you can do with just one equation. You should differentiate it and then try to eliminate some of the variables with the equation that appeared first. Okay, so let's just do that. Okay, so my derivative is always going to be delta, or maybe, I mean, at a certain point there will be more than one derivative that always commute with each other. But let's differentiate this equation, and we know the derivative of this equation is going to be 0 since this is 0. So, okay, so by calculus, I guess, we'll use the chain rule on the first term.
Product rule.
Or the product rule, yeah, sorry. No, I don't teach calculus. Yeah, sorry. Gosh. Now I use it.
Oh, I feel like I'm in my calculus class now. Yeah, now it's just, yeah.
Okay, so it looks like I get that, right? Okay, so now, if I cancel out some terms, I get 2 delta x times delta to the 4th x minus 1. Oh, now you see why I chose that. Right, okay. So this equation vanishing means that delta x has to be 0. That means that this term is 0, and that means that this term is 0, and that means that x has to be 0. Okay, so x equals 0 is the only solution to this system of one equation and one inequality. And you can see it's somehow it's not completely transparent just staring at it that this would be the case, but it is. Okay, so, all right, so we need a way to formally think about this in a systematic way if we're going to have any hope of getting a bound of the form that I'm talking about. Okay, and so that's more or less what Omar and I are going to talk about today. I'm only going to talk about one part of that problem. And the part that I'm going to talk about is really, I guess, what I would consider the more algebro-geometric portion of the problem. And Omar's going to talk about a separate sort of differential portion of the problem. Okay, but really both of them are intertwined. Okay, and so it's just so you think that, you know, there's some real reason to do this. You know, what are the real sort of, I guess, okay, look, you might not consider this a serious reason to study this problem. I mean, I just told you I did this computation on a plane. I mean, doesn't rule out the fact that it might be interesting. But you might want to know, are there any serious motivations behind this sort of thing? And the answer is, I mean, for me, various other people have various different answers. But for me, part of the motivation is that basically this problem will, in certain cases, this sort of bound gives effective, and by effective I mean an actual number that you can calculate, gives effective bounds for the sizes of certain, what I'll call unlikely intersections. And so far, all the examples all the examples that I was motivated by are special cases of what is called the Zilbert-Pink conjecture, which I'm not going to state because it's not the topic of this talk, but they're related to this thing called the Zilbert-Pink conjecture, which is sort of a simultaneous generalization of statements like Mordell-Lang and Andre Oort. And so, for instance, this kind of reasoning is what gives you effective bounds for the number of points on some non-torsion translate of of an abelian subvariety when you're thinking about Mordell-Lang type problems. I mean, so this is behind, you know, the effective bounds that you get from Reshofsky's methods, and it's also behind the effective bounds that you get for certain cases of Andre Oort, which I'm also not talking about today, which Tom Scanlon and I have worked out. Okay, so this is not what the talk is about. I just want to say there's some non-plane motivation.
Jim?
Yes.
If there are only finitely many solutions to a system like that,
yeah,
will you eventually realize it? That there are only finite? I mean, is there always some way of doing, you know, combinations, differentiating, whatever?
Well, that's what this talk is about.
Okay.
Yeah. Yes. Yeah, the answer is yes. The answer is yes, and it's a question. I mean, there's sort of two questions. You have to you have to know how to calculate degrees of certain things, and you have to know how far to differentiate. And I'm going to talk about how to calculate degrees of certain things, and Omar is going to talk about how to differentiate.
But I wasn't even asking for the uniform bound or anything. It was just, you know, will you eventually realize their own fundamental?
Yeah, you would, and I think you could probably get that. You can get that from various.
Is it actually final resolution for? Well,
Can you calculate the
When
dimension?
you get a
That's what you're
bound,
asking.
then you can of
Yeah.
course
Can you
decide.
calculate the dimension? That's a bit
After you exceed the
difficult.
bound, you define it, and
Definable property.
Yeah.
How's that again? So
Yeah, finiteness is a definable property. That's some people would call that model theorists would call that the non-finite cover property in a given theory. DCF has the non-finite cover property. There's a old proof due to allow band injuries, and you can regard what I'm doing as an effective version of NFCP.
That's exactly.
That is what we're doing, stated in model theoretic terms. Okay, so if you want more examples of of differential equations that have finitely many solutions, I can give more.
Jim, you can also test that on Maple.
Yeah. Okay. So, all right. Well, Alexei can test it in Maple. I'm not saying I can't. Okay. So, all right. So, I want to talk about a way to sort of algebraize, I guess I would say, a problem in differential equations. I'm going to be talking about degrees of certain algebraic varieties, affine algebraic varieties, and so, I'm going to have to give a formal definition of them, but I also want to just explain to you what I'm talking about first. Okay, so in an informal way. Okay, so let's say that you're given an affine variety. Okay, and so for me, I'll take V to be irreducible. I'll take V to be the zero set of some collection of polynomials in this way. Okay. So I think if you want to think about sort of if you want to think about some associated things that you get at from the differential world, things that I'm going to need to think about in this talk, but you just want to think about things of some what I call bounded order. There's two natural things to do, okay? And so let me fix U large model of DCF. I'm just going to have one derivation right now for this discussion. So I think that there's two natural things that you'd want to think about if you were going to think about.
Yeah. By the way, so not everyone in this audience is familiar with the model theoretic language.
Okay, yeah. So this is a differentially closed field, and it's universal over the field of definition of V or any finitely generated differential field extension.
So the F's are differential polynomials?
No, they're just polynomials at this point.
Oh, okay.
But I want to think about the points in some large differential field.
Okay.
Okay, so there's sort of two things that I think are natural to think about. So the first thing is that you could think about an associated algebraic variety where you just look at the derivatives of some bounded order of the F's here. Okay, so if you have something like f of x equals 2x squared, okay, of course you can see already that I can differentiate things in the polynomial ring. So I can take delta of f of x, and okay, so this is 4x x prime. And so I could think about in some higher affine space, the variety that I get by taking the zero set of the f's and some bounded number of derivatives of the f's. Okay, so intuitively, I hope that makes sense, but I'll write down what I mean. So I could think about what I will in this talk call tau sub L V as a subset of a to the n times L plus 1. And I'll define this to be the zero set of, well, the F1, and I'll say what variables I'm using here. And okay, and so hopefully you see that I'm running through delta to the L of F, whatever I have, K.
So you're doing ordinary?
Yeah, I'm just in the ordinary case now, because I'm just trying to give an intuitive explanation of there's going to be two different algebraic varieties, and I want you to intuitively understand what they are before I give some formal definitions. Although
you didn't write it down, but you did say it. V is irreducible.
Yeah, V will be irreducible here.
Okay.
Yeah. Oh. So I'm going to think about the variety which is cut out by this now, and now of course.
But so when x prime occurs, it's a new variable.
It's a new variable, yeah.
Okay, so it's a jet space. It's a kind of a jet space.
Yeah.
In fact, it's, well, you'll see what it is. But if V is defined over the constant field, then it's exactly the jet space. And if it's not, it's a torsor.
Oh, I see. Because I see.
Okay. And so I'll give a formal definition, but I want you to intuitively understand what objects we're dealing with first. So I'm thinking here of the variables as being, first, here is the original x bars. So this is an n tuple here. And then I'm thinking of delta of x bar. So I mean, delta applied to these guys. These are new formal variables up through delta to the L of x bar. And so, when I write delta of x bar, I mean applied to each index of the two. Okay, so I hope you understand at least what this variety is. Okay, of course, it's clear what the generators of the variety are. Okay, I mean, or the generators of the ideal, right? I wrote them down. If you give me these, I can produce these. That's easy. So the bad thing, or well, maybe the bad thing is that this definitely won't be irreducible, even when you start with V being irreducible. And
definitely, it might not be irreducible.
Oh, sorry. Yeah. Okay, you definitely cannot assume it to be irreducible. Okay, so things will work out well, and this will be irreducible when you start with a V that's smooth. But in general, it's not going to be the case.
Jim, are you thinking of delta of x bar as the actual derivative of x bar, or just are these coordinates in the algebraic solutions of those algebraic?
These are new formal coordinates, and I'm thinking of this. I'm thinking of this as an algebraic variety.
Okay. Yeah. Thanks.
Or if you like your varieties to be irreducible, I'm thinking of this as a closed subset of affine n times L plus 1 space. Okay? So this is one thing you can think of. The advantage of this variety is that you can calculate, you know explicitly things about it based on this. The bad thing about it is, well, okay, maybe you can't see this from this, but somehow it's not all clear. This seems like it could depend very subtly on the embedding. Certain properties, this could depend really subtly on the embedding of V in AN.
Well, the degree depends, because it depends on the degree of the embedding of V in AN.
Yeah, of course. And well, okay, so let's just leave it at that. There's certain things that this will be good for, but there's certain things where this is bad. Okay, the good thing about it is that you know what the generators of the ideal are, and you can calculate certain things about it. The bad thing about it is that it's reducible. Okay, so the other thing that you could think about is a bit different. Okay, so the other thing you could think about is the following. So you could take the set of now I'm gonna take u bar to be in u to the n, okay, and I could think about the set of u bar delta of u bar, and so here I really mean the derivative
Okay.
applied to that point.
That makes a difference.
Okay, so this right here, such that u bar is in V of u. Okay, so this right here is not an algebraic variety yet, but I could take its closure in the Zariski topology. Okay, so I'll try to be careful when I do things like this. That's the Zariski closure. And this is what I'll call B sub L. Sorry, I don't know, but B sub L of B. Okay, and so you might ask, what are the good things about this? Well, the good thing is that this is irreducible. So you can see, I mean, so it's easy to see B L of V is irreducible.
Without the quotient.
No, not without the quotient theorem, of course. Assuming the quotient irreducibility.
You don't need it.
That's the ish. Okay, so how do you see that? So if you're a model theorist and you don't know this theorem, what the quotient irreducibility theorem says is that if you start with a variety which is irreducible in the Zariski topology over a differential field, then it remains irreducible in the quotient topology. Okay, and so how can you prove that this is irreducible? Well, I mean, so the closure of this, if you just looked at this first coordinate and you took the closure, that's irreducible, and this is the graph of a function.
Yeah.
And so then you take the closure and it stays irreducible. Okay, so
We recognize algebraic geometers.
so you need to, you have to think about that maybe a little bit, but it's true.
Yeah.
Okay, so that's the ish part. Okay, all right. So this is the good part about this variety, and other things about it are not so good. I mean, so the things that are not so good is that it seems that it's not really obvious what generators for the ideal of functions which vanish on BL of V is.
What are you doing? Are you serious?
I'm sorry?
Are you serious? That's not obvious.
Yeah.
Not obvious.
It's not obvious.
Well, Maple
You
can
mean
find
the-
it.
Yeah, Maple can find it, but
Is it radical or just ordinary algebra? This is just algebra, right?
Algebraic ideal.
Just algebraic ideal.
Algebraic
Yeah.
Not the radical, not necessarily radical.
What?
no,
that'd
I'm only talking about this as a variety right
As
now.
a radical.
As a variety.
It's fine.
Okay,
It's a
yeah. Of course, you can
Yeah,
you
you
can
define
calculate
it's
it,
fine.
but if you hand me some generators here, it's not completely trivial for me to say.
Mathematica had trouble with the first prolongation.
It's not completely trivial for me to say
When I started the
what are the degrees and et cetera about the generators
Singularities.
of I of BL.
Yeah.
What do you mean, but you have a degree bound, so therefore you know the degrees.
Well, yeah, but I'm going to prove a degree bound in this talk.
Yeah, and from that you know what the degrees are, because it's an upper bound for some of the degrees.
I think obvious applies to us, not to you.
Okay, it's not obvious just by staring at the problem. I mean, from what I prove in this talk, it will be obvious.
Not obvious now.
No, yeah.
It's not as obvious as the other one.
Not obvious other to
look,
than to expect.
here I gave them to you. That's what I would call obvious.
That would be obvious.
They're not a priori, they're not a priori given. There's no way,
Yeah. Okay. So not okay. Maybe I should not given.
Singularities.
Okay. So
Yeah.
okay. I mean, and so the other thing is, and so I should mention okay. So for this problem in the ordinary case, so there was Rashofsky and Pillay in the late 90s worked on this problem, this original problem that I stated in the case of ordinary differential equations. And they calculated things about this variety here and about this variety here. Unfortunately, there's a mistake in their paper. Although their calculations are, I mean, their actual theorems are still correct. It's just that they make one claim which is completely false, which simplifies the problem. And so the thing that would simplify this problem is if you knew rather automatically that that BL of V had the same dimension as tau L of V. But that's not true. And so if you knew that right away, you would know that BL of V was a component of tau L of V. And then you could get information about BL of V from tau L of V. Okay? Here's why that's not true. Okay? So let me give another extreme.
Before you go on, it's not clear to me even that this tau L of V doesn't depend on delta. Delta is just formal. But their delta is a...
No. It does actually, because
It's just formal derivatives of polynomials.
It applies to the coefficients.
no, but you twist the coefficients.
Oh, you twist the coefficients.
Yeah.
Oh,
Yeah, so the coefficients, so I agree if the base field that you started with had a trivial derivation on it, then it wouldn't depend at all, and in fact this is the same definition as you would find in various places in algebraic geometry, truncated arc spaces or finite jet spaces. Goes by various
but that one, even in that situation, that one is not clear that it doesn't depend on the delta.
Right. Yeah. That's not clear, but I'll prove that it doesn't.
Okay.
Okay. And so that's part of what I'm proving. Okay. Proving that it doesn't, and so that you can still get properties of this guy here. See, as far as looking for solutions to differential equations which happen to lie on the Zariski closure of V, you can already see that only this BL of V is really going to be important somehow, because every solution to a differential equation whose Zariski closure, for a differential variety whose Zariski closure is contained in V, is going to have the property that if you differentiate its points, they'll lie in here.
Right.
Okay, so this variety here is somehow used. This is some sort of gadget which makes computations convenient, makes proving things convenient. But this is the thing that you're really interested in studying if you're trying to do differential algebra. Okay. All right. So, let's give an example which shows us. So in fact, let's suppose that we're working with a variety which is defined over a differential field with a trivial derivation. Okay. So then to people who are doing more algebraic geometry, this object here will become more familiar. And so this is a fact. When V is defined over K and delta of K equals 0, tau L of V can be defined in the following manner, and we'll get to things more like this in the rest of the talk, is the variety which represents the K, sorry. So, which represents the R of T mod T to the L plus 1 points of V. So let me set this up. So for any okay, I'll take R to be a ring extending which contains K, because I don't want to start taking tensors too much, but I don't want to do any base change. So in other words, what I'm saying is that V of R what I'm saying is that for any ring, the R points of V, so if you just want to think about K, that's fine. Just do that, okay? So the K points of tau L of V correspond to the K of T mod T to the L plus 1 points of V, of the base variety. Okay, in the same way that because tau 1 of V, in this case, is the tangent bundle points of for some field K correspond to the dual number points on the variety. Okay?
What if it has singularities, the variety?
This is still true.
It's not just the tangent bundle, but it has extra, that part, I
That's
see.
all Nash's problem.
Yeah, I see.
So that's Nash's problem, to find the singularity.
Yeah, Nash's problem.
So I think it's instructive to see an example of this, of why this sort of fact is useful for thinking about things. And I'll give an example that I usually like to give. That I usually like to think about if you're trying to think of counterexamples, which shows that in general, BL of V can be smaller dimensional than tau L of V. So I guess I'll work in A3, and I want to look at this variety. Of course, the problem is there's a very bad singularity at the origin.
Yeah.
And x squared plus y cubed doesn't give you the example?
No, because in that case, tau L. No, it gives you an example, but not one where the dimensions are different. One where there's an extra component. But I want one where the dimension of.
So when I was calculating, okay, I'll tell you later about it. Because at least its dimension. So the result in Annan's paper that shows how the dimension grows when you prolong.
Yeah.
Okay, so for x squared plus y cubed, the dimension.
Do you mean in A2 or in A3?
X squared plus y cubed.
Doesn't make a difference, because that's
It doesn't matter.
So I think from the third to fourth prolongation, the dimension jumps by 2.
Okay, I can believe that, but I don't know an example. I don't know an example of this sort of behavior that's simpler than this at the first prolongation.
I said this. This will be first prolongation.
That's the first prolongation.
No, it won't. You're right. Okay. Well, I like this example because it's easy to calculate. Let's just.
That's your example.
Okay. So, no. Do I want this? I want to the third power, maybe, right?
Okay.
Don't you think, Omar?
You want to go to a third
Don't
formulation?
you think I want this to third power, don't I?
Do you want to go to a third formulation when you do those type of things? You want four.
Okay,
Let's start with
three might be 4.
Works with 3, it's 3.
Next time, man. Let's see what happens.
That's a Fermat curve. That's a nice name. The cone on the Fermat
That's always a good name on something.
Yeah, I want 4. Sorry. Okay, and so I want to think about this as giving me V. This is V, and I'm going to think about tau 3 of V. And so by what I said here, I can think of that, and okay, it's a little loose, but you can think of that as, and I just want to think about the K points. I'll assume I'm working over some algebraically closed field K. So you can think of this as the K of T mod T to the 4th points of V. So what does that look like as a variety? So you write this in coordinates as, okay, so you have A0 plus A1T plus A2T squared plus A3T to the 3rd. And here, B0 plus B1T plus B2T squared plus B3T to the 3rd, and C0 plus C1T plus C2T squared plus C3T to the 3rd. Okay, so the points are going to look like that form. You can think of them in that form. And now, let's look at the equation. And now think what happens if I work over the origin so that A0, not A0, B0 and C0 are all 0. Then no matter what I put in for A1, for those guys, I satisfy that equation.
Right.
Because I'm working in T, I'm working modulo this idea, right? So this, for arbitrary, AI, BI, CI is on tau L, tau 3 of V. And so that means that tau 3, I mean, this is a copy of affine 9 space, right? So the dimension of tau 3 of V is 9. Okay? I mean, you can prove that. I guess I've showed you that it's at least 9.
You're right, the other points are regular points. So
the other points are regular points, and so if you're away from that point, then the fiber above every other point in tau 3, it has dimension 8.
Yeah.
Okay? It does. I also calculated this on the plane. Okay, so
the fiber has dimension 6, no? The fiber. Well, doesn't matter.
Sorry, yeah. The fiber has dimension 6. The total space above the smooth locus has dimension 8. That's what yeah. Okay. I calculated that one. Okay, so that's an example which shows you have to prove something if you want to get, see, what we want, okay, fundamentally what I want to prove is a degree bound for BL of V. Okay, and I have to prove, since I don't know in general, it's not obvious to me how to write down generators for BL of V or to get degree bounds for them and things like that. Where I want to get that bound from is from tau L of V, where it is obvious.
You haven't computed the BL.
Now I haven't computed the BL, but you can already see that the BL has to have dimension 8, because if you think about it, X, Y, and Z, those guys are algebraically dependent, so they're transcendence degree 2. Then I differentiate. Their derivatives satisfy the derivative of that algebraic relation. So that's transcendence degree 2. Differentiate again, 2 more transcendence degrees, and again, 2 more. Right? If I started with something sufficiently generic, so that means dimension 8. So BL of V has dimension 8. And so, and Alexei, you say that you have an example that's somewhat simpler where this behavior also
At
happens.
least the dimensions are smaller. But the number of prolongations, maybe, I saw the number of 3 or 4. I did the calculation on my own.
Okay.
I can show it to you later.
Okay, good. So, what is this related to? It turns out that the dimension of tau L of V is related to a basic invariant of the singularities on V called the log canonical threshold, which is reciprocal to Arnold multiplicity. I'm not going to say anything. Okay. And so if you can calculate the log canonical, let me just make one other remark about this dimension. If you can calculate the log canonical threshold of the singularities on your variety, then you can calculate the stages at which the dimensions of tau and BL differ. That's a theorem of Mustatsa. Okay, so you can, well, okay, that's not literally a theorem of Mustatsa. It's a theorem of Mustatsa when V is defined over a trivial differential field, but you can prove the theorem in general by some twisting argument.
By the way, I don't think you've said that one is containing the other, right? I mean, it's pretty clear. But
Yeah, but it is clear that BL is contained in tau.
yeah.
I think I did say that, right?
No, you
I
actually
didn't.
didn't. I was actually wondering about that.
yeah, that's
Okay.
Yeah.
So at this point,
That's the chain rule.
is that what the chain rule?
That's what the chain rule is.
That's what the chain rule is. Okay.
Always useful, that.
Okay. So. Okay. So. Yeah. So the question is.
So which part? What?
BL is containing tau.
So what's the relation between the coefficients to cut down from tau 3 to BL3 to B3?
I'm sorry. What's the
relation between the AIs and BICIs so that you could cut down from T3 B, that 9 dimension, into BL3 8 dimension? Is it something hyperplane or?
Yeah, I mean, you see, when you're taking derivatives of the points, it's somehow, and you start with just like an isolated point, like a singularity in this case, it's somehow very different on the points side than on the ideal side, right? Because if I start with 0, 0, 0 and I take its derivative, the derivative is 0, 0, 0. So I just get 1 point.
Yeah.
And so.
Oh, so you're saying not that uniform.
William, so if you want to calculate,
Yes.
so in the language you prefer,
Yeah.
so just take the polynomial, take its prolongations after that order,
Right.
and saturate by this initials by seconds. And so that take that polynomial ideal,
Yeah,
depending
that
on the
gets
weight.
the, what I call the general.
What exactly this calculation will show.
Okay.
Yeah. Okay. So.
Yes.
But that's precisely the prolongation of the prime component.
See that? Yeah.
Yeah.
Oh, I'd like to see that.
Okay, so let me just say, I think it's probably not wise in the interest of time to go through. Okay, so there's a systematic development of these tau functors of, I'll call, prolongations. Even in greater generality than this, due to Musa and Scanlon. And, okay, and basically, the thing that ultimately is going to let me get degree bounds for BL comes from applying their work. But let me just try to give you a sense of how they define this. So they define this tau L is a functor from, let's say, K varieties. mean, look, they define this in much greater generality, but it's a functor from affine K varieties, affine K varieties. I guess let me say that some important facts about it are that, okay, so I mean they do this, which in some way represents, again, the K of T mod T to the L plus 1 points on V, but twisted in some way. Okay, and I think it's probably not wise to, in the interest of time, to go through the formal definitions, but if you're familiar with such things, the way that it's defined is by using V restriction. Okay, so you
Do they assume K is constant?
No.
No.
That's why I wrote twisted.
Yeah.
Yeah, I realized that when you got to there, but then you said earlier K was the field of constants of U.
Yeah, no, I don't want to assume that anymore. K is a big differential field at this point.
Yeah.
Some differential field.
Okay.
Okay, and some important facts about the setup are the following. So when you have a map from V to
So you're saying that these are representable functors still?
Yeah, these are representable functors. Yeah. So sorry if I didn't say that. Yeah, and they're represented by an affine variety. Okay. So yeah, and you could do this more generally, but you can't do it arbitrarily. If you look at what you have to assume to apply V restriction, it's basically you can do it for those schemes. But it certainly applies to affine things. I can't remember the most general setup in which you can do it.
So I have,
Yes.
so run quickly the examples for x squared minus y cubed. For prolongation 4, dimension is 5. Prolongation 5, dimension is 7.
Okay. All right.
That's
Great. Yes. So Alexa is another example. Very good. Okay. So facts. It respects. I mean, you might kind of gather this, but it respects a holomorphism. So you get a naturally induced map tau L F from tau L V. Okay, so if this is a tau, then this. Okay, so that's one thing, which is somehow useful. Okay, so if V is smooth and absolutely irreducible, I don't want to write that, I'll just assume it, and dimension V equals D, then tau L V has very predictable dimension growth is D times L plus 1, and is smooth.
Is it actually locally driven fibrilation?
Yes.
Yeah.
Yeah.
It's the same thing as in
the smooth case. Yeah, you can think of it as a higher order tangent bundle or a torsor of the jet space.
Yeah, but I mean with the twist, even with the twist, I don't know how.
Even with the twist,
Okay,
yeah. It's a theorem. Well, say it's a theorem.
Jim, this fact is true because then BL is equal to tau L.
Yes, BL. Yeah, and
Is that why this?
yes, of course. Yeah.
Yeah.
So good, very good. So of course, since we know that BL has that dimension,
Yeah.
then they're equal.
As a consequence, you got that.
Yeah. Okay. Are there? Okay. All right. Okay. So, okay, and so So I'm not claiming that that I can in general, just given any old v, which might not be a complete intersection, say, and probably won't be smooth. I'm not claiming that I could calculate necessarily the degree of tau L of v, but I can in one important circumstance, which is what I'm essentially going to use. So when V is a hypersurface, of course, the degree of tau L of V is exceptionally easy to calculate, right? So, what is it?
At most.
Well, in most. In most. Bound. Always bound.
Oh, okay.
Yeah, so it's...
Otherwise, it can be anything from there to the bound.
Pardon me?
It could be more or less anything from...
Yeah. Okay, so did I specify a degree? Okay, so let's say degree of F equivalent to degree B is D1, then this is less than D1 to the L plus 1. All right, so...
The bound is sharp.
Pardon me?
And this bound is sharp.
This bound is sharp, of course. Yeah. Okay, so so again, my goal in this talk. So the goal is to bound the degree of BL of V in terms of degree of BL of V. Sorry, in terms of V. Okay, and so
For hypersurface?
no, in general, but here's how I'm going to do it. So the first claim is there is a birational map from V to some V1 where V1 is a hypersurface such that degree of V1 equals the degree of V. That's not so hard, but the degree, and for all L, the degree of BL of V1 equals the degree of BL of V.
What? I don't understand. Is this claim... Could you check the claim again? Is this what you had in mind?
So you may assume V is hypersurface.
Yeah, if you suffices to grab the surface.
And then you have
Then you have that.
Oh,
Then you
what's
have to
it-
prove
what's the
something
question?
about how BL since it sits inside tau L.
you just
V is an arbitrary variety, an irreducible variety.
This is all in
So
general
1 point is
smaller.
okay.
But
The degree of BL.
it's not enough that it's not enough that it's a subset has to
I don't
be a
understand.
component.
Yeah, one point is fine.
So
Then I'll
once
take
you get
the
a component,
morphism
yes.
to a point in
I can
A1.
see.
Yeah, you need to see that.
For a finite collection of points, this is...
But by rational you don't mean that V1 is... Okay, I see, okay.
No, you said you have the same function. That's what
They have the same function field, yeah. Okay, so what's the map? I mean, the proof is, I say what the map is, okay? And so the trick is, of course, not, okay, look, you can do this by taking a generic enough projection. Okay, but you have to think a little bit more because this depends on the differential structure of the situation. Okay, so you have to think a little bit more for this, but